The air inside this facility carries a faint sweetness, barely noticeable beneath the mechanical hum of conveyor belts stretching toward distant shadows. Somewhere in California's Central Valley, hidden behind ordinary industrial walls, billions of almonds move through a choreographed transformation most consumers never witness. This isn't just a processing plant. It's a precision ecosystem where raw agricultural output becomes the world's most valuable tree nut commodity, shipped to over 100 countries before most people finish their morning coffee. You're standing at the threshold of an operation that handles approximately 80% of the planet's almond supply. The numbers are staggering. California alone produces over 2 billion pounds of almonds annually, yet few understand the invisible infrastructure converting orchard harvests into the perfectly uniform kernels lining supermarket shelves worldwide. Every almond you've ever eaten passed through facilities like this one, subjected to processes designed by food scientists, agricultural engineers, and quality control specialists working in concert. The factory floor ahead resembles something between a pharmaceutical laboratory and an aerospace assembly line. Stainless steel dominates every surface. Computer monitors glow with real-time data streams. Robotic sorters operated by artificial intelligence scan passing almonds at speeds human eyes cannot match. This convergence of agriculture and advanced technology represents decades of innovation, billions in infrastructure investment, and California's evolution into the undisputed almond capital of Earth. What began as experimental orchards in the 1850s now powers a $12 billion industry, and everything flows through facilities exactly like the one surrounding you now. The journey from tree to table involves more science, more precision, and more hidden complexity than most people imagine. You're about to discover why. Most almonds begin their transformation covered in dust, fragments of hull material, and the evidence of mechanical harvesting. Some arrive with shells already cracked. Others carry microscopic bacteria from the orchard environment. The facility's first responsibility involves eliminating every contaminant, every imperfection, every potential safety hazard. What emerges on the other side must meet standards so rigorous that a single failed batch can trigger international recalls affecting millions of consumers. The stakes are enormous. The processes are fascinating. And the story hidden inside these walls reveals how modern food production operates at a scale and sophistication most observers never suspect. Before diving into the mechanical intricacies, consider what makes almonds extraordinarily unusual among agricultural products. Unlike seasonal fruits or vegetables that flood markets during narrow harvest windows, almonds require exactly one growing region with one specific climate pattern. California's Mediterranean-style weather, wet winters followed by hot, dry summers, creates the only significant commercial almond-producing zone in the United States. This geographic monopoly concentrates immense economic power within a relatively small area, making facilities like this one critical nodes in global food distribution networks. The almond itself is botanically bizarre. It's not technically a nut at all, but rather the seed of a drupe fruit, making it a distant cousin of peaches, cherries, and plums. The hard shell consumers rarely see protects this seed inside the fuzzy green hull that splits open on the tree when almonds reach maturity. Ancient civilizations cultivated almonds along the Mediterranean and Middle East for millennia before Spanish missionaries introduced them to California missions in the 1700s. Those early plantings struggled. The trees remained curiosities until the late 19th century when enterprising farmers recognized California's climate potential and began serious commercial cultivation. Today's almond industry barely resembles those pioneer efforts. Modern orchards function as biological factories, with each tree positioned for optimal sunlight exposure, irrigation efficiency, and mechanical harvesting access. Growers use advanced drip systems that deliver precise water quantities directly to root zones, reducing waste while maximizing yield. They employ satellite imagery and soil sensors to monitor crop health in real time. During bloom season in February, they rent commercial beehives by the thousands, trucking in pollinators from across the continent to ensure maximum pollination success. Without these managed bee colonies, California's almond orchards would produce virtually nothing. The symbiosis between industrial agriculture and managed pollination represents one of the largest annual migrations of living creatures in North America. The though it happens largely out of public view. Harvesting occurs between August and October, depending on variety. Specialized machines called shakers grip tree trunks and vibrate them with enough force to dislodge ripe almonds without damaging branches. The nuts fall onto the orchard floor, where they remain for days, drying naturally under California's intense summer sun. This field drying phase reduces moisture content from around 30% down to approximately 6%, creating the stable conditions needed for safe storage and processing. Once dried, mechanical sweepers gather the almonds into windrows, long rows running between tree lines, before pickup machines vacuum them into collection carts. The almonds arriving at processing facilities have already survived multiple quality checkpoints in the field, yet they're still far from ready for human consumption. Subscribe now to explore the hidden world of industrial food production, and hit the like button if you're fascinated by the engineering behind everyday products. Here's something most consumers never consider. Almonds are one of the most water-intensive crops in California agriculture, requiring approximately 1 gallon of water per individual nut from bloom to harvest. With over 6,000 almonds per pound and billions of pounds produced annually, the math becomes staggering. California's periodic droughts have sparked intense debate about agricultural water usage, pushing the industry toward increasingly sophisticated irrigation technologies. Modern almond farms use soil moisture sensors, weather data, and computer modeling to minimize water waste while maintaining productivity. Some operations capture and recycle tailwater, the runoff from irrigation, using it multiple times before it finally percolates into groundwater aquifers. These innovations emerged from necessity, driven by both environmental pressure and economic reality in a region where water scarcity defines agricultural possibility. The almond processing facility serves multiple critical functions simultaneously. It cleans incoming nuts, removing field debris and contaminants. It shells almonds, separating kernels from their protective casings. It sorts kernels by size, color, and quality grade. It detects and eliminates defective nuts using advanced optical technology. It applies food safety treatments to eliminate potential pathogens. And it packages finished products according to customer specifications ranging from bulk industrial containers to consumer-ready retail packaging. Each function involves specialized equipment, trained operators, and quality control protocols designed to maintain consistency across billions of individual almonds. Incoming loads arrive in massive trucks carrying anywhere from 20 to 50,000 pounds of in-shell almonds. Upon arrival, samples undergo immediate testing to assess moisture content, foreign material levels, and overall quality. Facilities reject loads that fail to meet standards, sending them back to handlers or diverting them toward lower-grade applications like animal feed or almond meal production. Accepted loads proceed into storage silos where temperature and humidity conditions remain carefully controlled. Almonds are hygroscopic, meaning they readily absorb or release moisture depending on environmental conditions. Too much moisture invites mold growth and aflatoxin contamination. Too little makes kernels brittle and prone to breakage during processing. The balance must remain precise. Shelling begins with mechanical cracking systems that apply calibrated pressure to fracture shells without damaging the kernels inside. Modern crackers achieve this through precisely engineered gaps and roller speeds, adjusting automatically based on shell hardness and nut size. The process sounds simple but requires extraordinary precision. Too much force pulverizes kernels into unusable fragments, while insufficient force leaves shells intact. Shelled almonds and shell fragments then proceed to separation equipment using a combination of air currents, vibrating screens, and density differences to isolate clean kernels from debris. What emerges from initial shelling still contains imperfections, fragments of shell material, pieces of woody hull, occasional small stones from the orchard floor, and kernels with visual defects like insect damage, mold spots, or discoloration. This is where optical sorting technology becomes transformative. High-speed cameras photograph every passing almond multiple times per second, analyzing color, shape, and surface characteristics. Computer algorithms compare each nut against program standards, triggering pneumatic ejectors that blast defective almonds from the stream with precisely timed air bursts. These systems operate so rapidly that human observers see only a blur of movement, yet they're removing specific individual almonds based on microscopic visual anomalies. A single optical sorter can evaluate and categorize hundreds of almonds per second, achieving accuracy levels impossible through manual inspection. This size grading follows optical sorting. Almonds pass across vibrating screens with progressively smaller openings, separating them into categories ranging from extra large to broken pieces. Different markets demand different sizes. Whole almonds command premium prices for snacking and retail sales, while smaller pieces suit ingredient applications in bakeries, confectioneries, and food manufacturing. Nothing goes to waste. Even the finest fragments find use in almond flour, almond butter, or extraction processes that recover almond oil. The industry operates on thin margins, making complete utilization essential for economic viability. Beyond size and appearance, food safety represents the paramount concern. Almonds can harbor salmonella bacteria, as several outbreaks in the early 2000s demonstrated. These incidents triggered mandatory pasteurization requirements for California almonds sold in North America. Facilities employ various pasteurization methods, including steam treatment, dry roasting, blanching, and propylene oxide fumigation. Steam pasteurization exposes almonds to high-temperature steam for precisely controlled durations, achieving pathogen elimination without significantly affecting flavor or nutritional content. The process requires careful calibration. Insufficient heat fails to eliminate bacteria, while excessive heat damages kernels and creates off flavors. Facilities validate their pasteurization processes through regular microbiological testing, ensuring treatments achieve the required pathogen reduction. A blanching represents another specialized process for almonds destined for specific applications. Blanched almonds have their brown skins removed, revealing the pale kernel underneath. The process involves briefly immersing almonds in boiling water to loosen skins, then passing them through rubber rollers that gently abrade the softened skins away. Blanched almonds command higher prices due to their appearance and texture, particularly in confectionery applications where the brown skin might interfere with product aesthetics or flavor profiles. Some manufacturers prefer blanched almonds for consistency in baking applications where visual uniformity matters. The facility also handles value-added processing beyond basic shelling and sorting. Slicing equipment produces uniform almond pieces for specific culinary applications. Roasting systems apply precise temperature profiles to develop desired flavor characteristics. Seasoning lines coat almonds with salt, spices, or sweet glazes according to customer specifications. Each additional processing step adds value while requiring specialized equipment, technical expertise, and quality control measures. A modern almond processing facility resembles a diversified manufacturing complex rather than a simple agricultural handler. Raw almonds arriving at this California facility begin their transformation in receiving bays where truck-mounted hoppers discharge loads into temporary storage silos. These silos maintain controlled atmospheric conditions, preventing moisture absorption and maintaining kernel quality during the queue time before processing. Automated systems monitor silo temperatures continuously, alerting operators to any anomalies that might indicate developing problems. Almonds can spontaneously combust under certain conditions when fine dust particles accumulate in enclosed spaces, making vigilant monitoring essential for facility safety. From storage, pneumatic conveyance systems transport almonds to the first processing stage, pre-cleaning. This initial cleaning removes the largest debris items, rocks, sticks, metal fragments, and oversized foreign materials that could damage downstream equipment. Scalpers and destoners use vibration, airflow, and density separation to extract these contaminants before almonds proceed to shelling equipment. The pre-cleaning stage handles enormous volumes rapidly, processing thousands of pounds per hour while maintaining careful separation between product and waste streams. Shelling equipment represents some of the most mechanically sophisticated machinery in the facility. Modern hullers and shellers employ multiple cracking stations arranged in series, each calibrated for slightly different nut characteristics. Almonds vary in size, shell hardness, and kernel-to-shell adhesion depending on variety, growing conditions, and maturity at harvest. Processing equipment must accommodate this natural variation while maintaining high efficiency and minimal kernel breakage. Engineers design these machines with adjustable gap settings, variable speed controls, and quick-change components that allow operators to optimize performance for different incoming loads. Shell separation occurs through a combination of mechanical and pneumatic sorting. Cracked shells and kernels flow across vibrating screens where air streams blow lighter shell fragments away while heavier kernels continue forward. Gravity tables use precisely angled vibrating surfaces to separate materials by density. Shells migrate toward collection points while kernels flow in different directions. The precision of these separation systems determines overall processing efficiency. Inadequate separation means valuable kernels contaminate shell waste streams, representing direct economic loss. Excessive processing to ensure complete separation can damage kernels, again reducing value. Operators constantly balance these competing demands. Following shell separation, kernels undergo electronic sorting using color cameras and near-infrared sensors. These systems detect characteristics invisible to human eyes, including internal defects, moisture variations, and subtle color differences indicating quality problems. The technology derives from systems originally developed for mineral sorting in mining operations, adapted for food processing applications. Each sorting pass removes additional defects, gradually refining product quality to meet increasingly stringent standards. Premium grades may pass through multiple sorting stages, with each pass removing smaller percentages of borderline kernels until only the finest products remain. Sizing equipment separates almonds using screens with specific opening dimensions. Standard sizing categories follow industry conventions measuring kernel length in fractions of an inch. Categories like 23/25 indicate nuts that pass through a 23/64 inch screen but not a 25/64 inch screen. These precise sizing standards allow manufacturers purchasing almonds to specify exactly what they need for particular applications. Confectioners making chocolate-covered almonds might require 27/30 sizing for visual consistency, while bakeries producing almond flour may prefer broken pieces and off-grade kernels that sell at significant discounts. Pasteurization equipment varies depending on the chosen treatment method. Steam pasteurization systems expose almonds to pressurized steam in sealed chambers, holding them at specific temperatures for validated time periods. The process requires careful moisture management. Steam adds moisture to almonds, which must then be carefully dried to restore proper moisture content without over-drying kernels. Drying systems use heated air flowing through perforated beds of almonds, removing surface moisture while monitoring kernel temperatures to prevent heat damage. The entire pasteurization and drying cycle might take 20 to 30 minutes from start to finish. Quality assurance laboratories within the facility conduct continuous testing throughout processing. Microbiological testing verifies pasteurization effectiveness. Moisture content testing ensures product stability. Foreign material screening confirms contamination controls work properly. Aflatoxin testing detects potentially dangerous mycotoxins that can develop if almonds were stored improperly before processing. These laboratory functions operate around the clock during harvest season, analyzing hundreds of samples daily to maintain quality assurance confidence. The lab results directly influence processing decisions. Detecting problems early allows operators to adjust equipment, rework substandard product, or segregate questionable lots before they contaminate larger batches. Packaging represents the final processing stage before almonds leave the facility. Industrial customers receive almonds in bulk containers, corrugated totes holding 2,000 pounds, super sacks containing 1 ton, or truckload quantities in food-grade bulk bins. Retail packaging lines fill consumer-sized bags, cans, or jars using automated weighing and filling equipment. Each package receives printing indicating processing date, lot codes, and traceability information linking back to specific harvest loads and orchard sources. This traceability allows rapid responses if quality problems emerge later. Facilities can identify and recall specific lots without disrupting entire production runs. The facility operates under multiple regulatory frameworks simultaneously. The Food and Drug Administration enforces pasteurization requirements and general food safety standards. The U.S. Department of Agriculture oversees grade standards and inspection programs. The Almond Board of California, a quasi-governmental organization funded by grower assessments, implements quality and food safety programs specific to the almond industry. International customers often require additional certifications: kosher, halal, organic, or country-specific import requirements. Meeting this regulatory complexity requires dedicated compliance staff, extensive record-keeping systems, and periodic third-party audits verifying that facilities maintain required standards. Environmental considerations increasingly influence facility operations. Water usage, energy consumption, and waste management all face growing scrutiny from regulators and consumers. Modern facilities incorporate water recycling systems, energy-efficient equipment, and comprehensive waste reduction programs. Almond shells and hulls, once considered waste products, now serve as valuable co-products. Shells provide livestock bedding, landscaping mulch, and increasingly, biofuel feedstock. Hulls contain enough nutritional value to serve as cattle feed supplements. This circular approach transforms waste streams into revenue sources while reducing environmental impact. Automation continues advancing throughout almond processing. Robotic systems handle packaging tasks formerly requiring manual labor. Artificial intelligence optimizes sorting parameters in real time based on incoming product characteristics. Predictive maintenance systems monitor equipment performance, scheduling repairs before breakdowns occur. These technological advances improve efficiency, reduce labor costs, and enhance product consistency. Yet they also require substantial capital investment and technical expertise to maintain. Smaller facilities struggle to compete as processing increasingly demands sophisticated technology and economies of scale. Beyond California's borders, international markets consume approximately 70% of the state's almond production. European Union countries, particularly Spain, Germany, and the Netherlands, import massive quantities. Asian markets, especially China and India, have grown rapidly as rising incomes increase demand for premium nuts. Middle Eastern countries maintain long-standing almond consumption traditions. This global distribution network requires sophisticated logistics, temperature-controlled shipping containers, customs documentation, phytosanitary certificates, and quality maintenance during transit times that can extend weeks or months. Almonds leaving California facilities today might not reach final consumers for half a year, requiring exceptional stability and quality retention throughout extended supply chains. So the next time you grab a handful of almonds, remember the invisible infrastructure behind those perfect kernels, the orchards engineered for optimal yield, the managed bee colonies ensuring pollination, the harvesting equipment vibrating trees with calibrated force, the field drying under intense summer sun, the processing facilities orchestrating dozens of operations simultaneously, the optical sorters evaluating individual nuts in microseconds, the pasteurization systems eliminating invisible pathogens, the quality laboratories testing continuously, the packaging lines preparing products for journeys spanning continents and months. But while almonds travel from California farms to worldwide markets through this intricate system, another agricultural product follows an equally fascinating path from field to finished goods. Have you ever wondered how the cotton in your t-shirt transforms from fluffy bolls in southern fields into the comfortable fabric you wear every day? That process involves secrets even more surprising than what you just discovered about almonds. The video that just appeared on your screen reveals the complete journey, including the hidden step that happens inside a facility most people will never see. Make sure you're subscribed so you don't miss future episodes exploring the hidden world of manufacturing. We are uncovering the processes behind products you use every single day but never think about. And here's a question for the comments. What surprised you most about almond processing? The water requirements, the AI-powered sorting technology, or the fact that almonds aren't technically nuts at all? Let us know below.